Hello, everybody. Let's start today. Today, we are going to start with recursion. The first problem that we'll be doing is validate BST. So what's a BST? Firstly, getting into the... Anybody? How do you define a BST? Gautam?
It's a binary search tree wherein we divide the array into half. We divide the search space into half, and every time we iterate, we try to reduce the search space by half and try to sort out the.
Anybody else? That's a good start. What is a BST?
The left side elements are smaller than the right side elements.
The left side elements are smaller than the root. All right, everybody Google. Find out what is BST. At this level, you should be knowing more about BST. Or just read the problem. That was enough for knowing about BST. All right, Shreya, what's a BST?
Sorry, that's what I'm trying to read towards.
Neil, can you help with BST, please?
Yeah, so as far as I know, like all the nodes for every node, left side of the node should be lesser than the node itself, and
Left
the right
should be,
side of the node,
and
lesser
right
than the
side.
node or greater than the root. Yeah.
Okay, and one more important point. Left, this doesn't complete the BST. One more thing about BST is what?
No duplicate values.
No duplicate
Left.
values. What? One
It
more.
should be a complete binary tree.
It doesn't need to be a complete binary tree.
Less
Google
than
it.
or
At most.
Just Google it. Complete BST is a complete BST. I've never said that. It's a complete
Left
BST.
At most 2 nodes.
less than or equal to root.
Left and right with should also be BST.
Left subtree and right sub. When we have no duplicates, then this should not be there, na? That if we are either this should not be there or this should not be there. If you are saying equality can be there, then you are conflicting with the other statement. All right.
Yeah.
Somebody was saying that okay, equal to if it is equal to, then I should not be writing this. Okay. All right. Left child should be smaller than the root. Right child should be greater than the root. I actually wanted to go into the next discussion about the BST, but surprisingly, it's the first batch that students are having doubts about the BST only. All right, left baby is lesser than the root, right baby is greater than the root, and I have every subtree is a BST. All right. So these are the 3 rules that we have. Can somebody tell me the values of a 4-level complete BST? Can somebody try to give a 4-level complete BST? Or just give it a good shot. Okay, what is complete BST? What does complete means?
Each node has their roots, left and right both.
Yeah, each node has left and right baby. All right. So 4-level BST, anybody? Vishal, do you want to give it a try?
4-level BST. Yeah,
4-level complete BST. Yeah.
So we have that means we have 4 levels, right? The like I mean 2 raised to 4 nodes will be there in the last level.
2 raised to 3.
So
Let's have 8 nodes.
this is 3, yeah. So first there are a root, and then there are two nodes, and then
Give me the root value.
they have
Give me the root value that you are thinking about.
1, and then we can have sorry, I mean we can have negative values, right?
You need to have negative values if you are starting with 1.
Yeah, 1, and on this side we can have -1 or 0. Left subtree.
Okay.
2.
Okay.
-1. Sorry, no. -5. You can say -5. On the left subtree of the 0, -5.
Okay.
The right. No. It cannot be. It has to be more than 0, right? So I guess root we can say we can take 10 or something.
Okay. Anybody else wants to give it a try?
I think we can start with 8, root node 8.
Okay.
And then left would be 4, 2, left 2, and 1. 3, 6, 5, 7. 5 and 7.
Good.
Yeah, then like 12, left is 10, 8 and 9 and 11, 14, 13 and 15.
But that's a good try. 4 level complete BST. And if I have to check whether it is a BST 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Perfect. It's a BST that we have. And it satisfies all the rules that we are talking about or given in the problem. That is, left maybe should be lesser than the root, right maybe should be greater than the root. And each subtree should be a BST. How do I determine whether it is a BST or not? Based upon 3 rules, either I can use 3 rules. Is there any other way that I can check whether it is a BST or not? I can check it with the 3 rules that we have. Left is smaller than the root, right is greater than the root, and every subtree is a BST. But other than this, is there any other way that we can check whether a BST is a BST or not?
We can print all the nodes and see if it's in sorted order or not.
We can print all the nodes. Okay.
I mean,
if
like
I print 8, 4, 2.
No, not like this.
Uh-huh.
Starting from the leftmost node, from 1.
Okay. So,
In order.
okay, if we do in-order traversal.
In order, sorry. Yeah, in order.
If we do in-order traversal should be sorted or ascending. What is in-order traversal?
Left subtree, root, and then right subtree.
Left, root, and right is in-order traversal. Is there any other traversal in trees? So in-order traversal is not only in BSTs, it's in all trees. All right?
Preorder, postorder traversal.
Preorder. Okay. What happens in preorder traversal?
Root comes first and left, right.
Root, left, right. All right. Any other?
Postorder traversal.
Postorder. Left, right, and
Right.
root. It's the position of the root that determines whether a traversal is in-order traversal, pre-order traversal, or post-order traversal. The BST's in-order traversal is always going to be sorted or ascending in order. This is also in order traversal only. Right, root, left. This is also pre-order traversal, that is root, right, left. This is also post-order traversal only, where we have right, left, and root. All right. The position of the root determines whether it is in-order traversal, whether it is pre-order traversal, whether it is post-order traversal. But whenever we are given a in-order, pre-order, post-order traversal, by default, we will be taking left comes before right. For example, left comes before right. Left comes before right. Left comes before right over here. Not the other way around. That right is coming before left, okay? The in-order traversal of a BST is sorted in nature, and that's what I did. When I was looking at this, I was doing 1, 2, 1, 2, 3, 4, 5, 6, 7, then 8, left down, root, then right subtree. In the right, left, 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 9, root, 10, right, 11, left done, root, 12. Then right subtree. In right, left one, 13, 14 is the root, and 15 is the right. All right. So in order traversal, left, then root, then right. That is the order that we are going to do. Now, we will go to the validating the BST. For example, one of the ways is that I can do the in-order traversal and I can check all these, I can put all these elements in a list and I can check whether it is ascending in nature or not. But let's put the validating the BST on the back burner for now. Let's focus on recursion. The nitty-gritties, the under the hood things of recursion. Each and everything about recursion we are going to learn. We write a recursive function on this tree. Let's call that function a helper, private helper. And we have tree node, root over here. Generally, the in-order traversal is written like this. That is helper, root dot left. Let's put system dot print. It's actually system dot out dot print. Let's call it up. And system dot print root dot value. And then helper of root dot right. And if root is equal to null, return. Let's call it 1. Let's call it line 2, line 3, line 4. Can somebody tell me what is this code written for? This is a very famous algorithm in BST.
In order traversal.
In order traversal. We are doing in order traversal, left, then root, processing of the root, then the write. All right. So this is in order traversal, but what we are going to do is we are going to do a couple of more things. Print down, print root down. And we have a stack, recursive stack. And we will be understanding the rules of recursion. And we will not be leaving any blind spot. Let's call it line 5. And we have to print the values over here. So what will be printed first? All right, firstly, when we start our recursion from here, what will be going inside the recursive stack? What will be there inside the recursive stack? Function.
Function calls.
Or function calls. Okay, yeah, it will be function call, but what will be the root at that time? Or. All right, anybody else? 8. Anybody else?
First frame will start root, right? 8, and then
right.
that calls 4, and then
functional call on 8.
That
node 8.
No, and then that goes.
If there will
that
be
goes to
function,
4.
just a moment. If there is a functional call on 4, where is the functional call of 8 remains?
That will be in the that will be still in this stack.
Not you. I'm talking to the students who are saying that, okay, functional call of 4 will be the first recursive call that I will be having. It means where is this functional call of 8? The initial functional call of 8.
Isn't the very first at the beginning of the function, isn't the root value as 8? So in line 2, when we put in root dot left, 4 goes in.
Okay, if 4 goes inside the stack, where is functional call of 8 in the universe?
It's still in the memory in the stack, like in the main. After the main functions stack frame, it will be function 8's stack frame, and on top of that will be function 4, the stack frame of function 4.
So the first functional call inside our call stack, which is going to act as a recursive stack over here, is functional call of 8. All right. So when we come, okay, anybody who can tell me what will be the order of prints over here? What will be the output of this function?
In order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Look at the print statements.
There will be up 1 and up 2, up 3, up 4, up in order.
Anybody else? All right, let's try to do it one by one together. Give full focus, okay? So function call of 8 will be the first function call. We'll go to line number 1. Is my root equal to null? We are at 8. 8 is the root. All right, then helper of root dot left. Recursion goes over here. Helper call of, that is functional call on left, is called 4. All right. We have returned from here only. We have gone to helper call. The earlier one still remains. That is there inside the stack. Then we come to line number 1 again. Is my root equal to null? Is this equal to null? No, it is not equal to null. In that scenario, we go to line number 2. That is roots left. 4's left is 2. There is a functional call at 2 now, which hits the function right here, line number 1, is my root equal to null? No, my root is not equal to null. We go to line number 2, helper call on 2's left, that is 1, is what is happening. All right, helper of 1, root is equal to 1. Is my root equal to null? No, root is not equal to null. We go over here, helper on root dot left, functional caller, null happens. We go over here, helper on null. Is my root equal to null? Yes, my root is equal to null. All right. When root is equal to null, from here, return happens. Return happens where? From where it was called. First rule of recursion, return happens to the same place where it was called. It's not about the place, but whatever functional call has happened from, if the functional call has happened from here, it will return to the same functional call without exception, without any second guesses. All right. So I'm going to write over here, just for your understanding, that all these functional calls have happened from line number 2 till now. Okay. They were left recursive calls. So when return happens, it returns to the same place from where it was called. It comes right here. Now this functional call is complete. Whenever a functional call is complete, what happens to the call stack?
It pops.
It pops. It pops. It has popped. That's why I'm putting a placeholder over here, that it pops. When it is complete, function call pops. Now when we are at line number 3, first thing that will be printed is, all right, let me write the rules of the recursion for now. It returns to the same place from where it was called. Pop happens. And 1:1 mapping with parameter. Now, it's not a rule of recursion. This is just for understanding that the other functional call is out. Now, at top of the stack, I have the functional call as 1. What is the root of functional call of 1? Where is the root now? At 1. This is my current root. So we call it 1:1 mapping just for understanding. But it is essentially, what is the functional call at the top of the stack? And the root over there was 1. Whatever has gone inside the stack will be the same thing that will be coming out of the stack. So root is equal to 1 now. System.out.print up will be printed. Up 1 will be printed. Up 1 will be printed. Once we have printed that in line number 3, then what happens?
We go again on
It goes
helper.
to the right side of 1.
Yeah, we go to line number 4 and it goes to the right side of 1. That is helper call of functional call on null happens. And it was called from which line? Line number 4. Helper of null happens. We hit helper of null. Is my root equal to null? Yes, my root is equal to null. Return happens. This is for the current functional call that the return has happened. Doesn't mean the whole recursive call will be complete. Recursion will not stop till all these function calls are there inside the recursive stack. Till that time, recursion will not stop. Now function call on null, the root is equal to null, return happens, returns to which place from where it was called? Line number 4. It returns to this place. What happens now?
Down one is printed.
Down one.
All right. Stack.pop again, because this function call is complete. So stack.pop happens. What is the root now? Again, 1. Function column 1. All right. Root is equal to 1. That is down 1 printed. Now we are going down over here. There is nothing. The function has finished over here. Or you can think of it as a return statement. Left of 1 is done, right of 1 is done. Left recursive call is done, right recursive call is done. Functional call on 1 is complete. Means return happen. Return will return to which place?
Root to
Return to the previous call.
Tell me the line where the
line 2.
Line 2.
It was called from line 2, it will return to line 2 on. All right. It returns to line 2. Stack.pop has happened. At the top of the stack, I have functional call on 2. So my root is 2 now. We are right here. What will be printed now? Up 2. We print in line number 3 up 2. And then right recursive call on 2 happens. That is, we go to 3. That is functional call on 3 has happened. From which line it has happened?
Line 4.
Line numbers. All right. This I am maintaining for your understanding. Okay. So when the function call is out, you know that at which line I have to return the control. This doesn't go inside the recursive stack. Only these go. All right. Up to, then function call on 3 happens from line number 4. Functional call on 3 happens, line number 4. Function call control comes over here. Is my root equal to null? No, it is not equal to null. We come to line number 2. Functional call on roots left. That is, functional call on null happens. And it happened from line number 2. Helper of null. We go over here. Is my root equal to null? Yes, it is equal to null. Return happens. Return returns to the same place from where it was called, line number 2. It comes right here. Pop has happened. Because this function call is complete, it will be going out of the call stack. What will be printed now?
Up 3.
Up 3.
Up 3. We come to line number 4. 3 is right. Call is done. That is 3 is right is null. Helper of null is done. Is my root equal to null? Function call on null is done. From line number 4, remember. Function call on null. We come over here. Root is equal to null. Return happens to the same place from where it was called. Line number 4. Stack.pop happens. This is out. What will be printed now?
Down 3.
Down 3.
Down 3. Why? Because this is a root now. Return happens now. That is, in English, left recursive call of 3 is done, right recursive call of 3 is done, functional call of 3 is done. When functional call of 3 is done, it means the return happens. Return happens to the which place?
Line 4.
Line number 4.
4.
It was called from line number 4, it will return to line number 4 only. All right. So it returns to line number 4, stack.pop has happened. This function call is complete. Stack.pop has happened. What will be printed now?
Down
Down
1.
2.
Down 2.
Down 2.
All right. Down 2 will be printed. And we hit the return statement again. That is function call on 2 is done. That is left recursive call of 2 is done. Right recursive call of 2 is done. Currently, here is the control of the recursion. Left recursive call is done. Right recursive call is done. We hit the return statement. Now, where is the control of recursion will go?
To the previous.
Tell me the previous. Tell me the line over here in the code, please.
Line number 2.
Line number 2. It returns to the same place from where it was called. It was called from line number 2. The control of the recursion will be going to line number 2. Stack.pop has happened. It means this function call is complete. This function call is complete. All right. What will be printed now? Up what?
Up
4.
4.
4.
Root is 4. Here is the control of the recursion now. Then root.write. Functional call on 6 is done. And that is now called from line number 4. Helper of 6. Helper of 6. Is my root equal to null? Is my 6 equal to null? No, it is not equal to null. Helper of root.left. That is functional call on 5 is done from line number 2. All right, functional call on 5. Is my 5 equal to null? No, it is not equal to null. The control comes over here. The code comes over here. Helper of root.left. That is 5's left is null. Called from line number 2. That is helper of null. Is my root equal to null? Yes. Return. Return returns to the same place from where it was called. Line number 2. This function call is complete. What will be printed now?
Up
Up
5.
5.
Up 5 will be printed. The code comes over here. Root.write. That is call on 5's right. Functional call on null. Called from line number 4. Helper of null. The code comes over here. Is my root equal to null? Yes. Return happens to the same place from where it was called. Line number 4. It returns over here. Stack.pop. This function call is complete. What will be printed now? Down 5. That is my current root. All right. And now we hit the return, or the function has completed. When we hit the return over here, we return to the same place from where the function call of 5 is complete. 5 was called. Remember, 5 happened. Left of 5, right of 5. Left of 5 is done, right of 5 is done. Function call of 5 is complete. We return to the same place from where it was called. It was called from line number 2. We return right to line number 2. This will be out. Somebody is not mute. Kindly mute yourself. We return to the same place. Stack.pop has happened. What will be printed? Up 6. Up 6 gets printed. Then root.write. Current root is 6. 6 right. That is, it goes right here. For the sake of time, I am deleting some of the nodes, okay? Let's take 9 over here, but 11 I can take. Okay. So I'm going to verse 7. Function call on 7, called from line number 4. Function call on 7. Is my 7 equal to null? Nope. Helper of root.left happens. Function call on null happens. It has happened from which line? Line number 2. Helper of null, root is equal to null, return. Return happens to the same place from where it was called. Line number 2. Stack.pop has happened. This is out. Now at top of my stack, function call of 7, that is root is equal to 7. What will be printed? Up 7. All right. Now 7's right. Function call of null has happened from line number 4. Function call of helper of null. Is my root equal to null? Yes. Return returns to the same place from where it was called. Stack.pop. Top of the stack, I have 7. That is my root. Down 7 will be printed. Return happens. It means the function call of left is done, right is done for 7. This function call is complete. Return happens. Return happens to the same place from where it was called, line number 4. This pops out. Down. Six will be printed. All right. Down 6 gets printed. Return. Return, it happens to the same place from where it was called, line number 4. This is the current control. Function call on 6 is done. Complete. Return happens. Return happens to the same place from where it was called. We have already noted down so that we don't get confused. It comes to the line number 4. Down. 4 gets printed. And the control of the recursion is at 4 right here. The left recursive call and the right recursive call of 4 is done. The function call of 4 is complete in English. If you want to see the code level control, down 4 is printed. This is complete. Return happens. Return happens to the same place from where it was called, line number 2. Stack.pop happens. What gets printed? Up 8. And here is the control of the recursion right now. Up 8 gets printed. Code comes over here. Root.right. Function call on 12 is done, and that is called from line number 4. I'm just going to delete this out. Then root.left. Function call of 12 is done. From line number 4, sorry. Function call of 12. Is 12 equal to null? No. Code comes over here. Root.left. 12 is left. Function call on 10 has happened. From line number 2. Function call of 10. Is my 10 equal to null? No. Left recursive call happens. Function call of null happens. Has happened from line number 2. Function call of null. Is my root equal to null? Yes. Return happens. It happens. Takes us to the same place from where it was called. It was called from line number 2. We'll return to line number 2. This is out. Stack.pop happens. This function call is complete. Control of the recursion is right here. Up 10 gets printed. Up 10 gets printed. Then we come over here. Roots right. Functional call of null has happened. From line number 4. Helper of null. Is my root equal to null? Yes. Root is equal to null. The Return happens to the same place from where it was called, line number 4. This is out. Stack.pop has happened because this function call is complete. Return has happened. Down 10 prints. Down 10 prints. Return happens to the same place from where it was called, line number 2. Comes over here. This is complete. Stack.pop has happened. Up. Well, gets printed. Up 12 gets printed. Root.write. Functional column. 12's right, that is 40. Has happened from line number 4. Helper of 14. Is my root equal to null? Is my 14 equal to null? No, it is not equal to null. We come right here. Helper of root.left. That is function call of null has happened from line number 2. Is my helper of null? Is my root equal to null? Yes. Return happens. We do hit the return statement. Return happens to the same place from where it was called. Line number 2. Stack.pop has happened. And up 14 gets printed. We come over here. Function call of null has happened. From line number 4. Helper of null. Is my root equal to null? Yes. It returns to the same place from where it was called. Line number 4. Stack.pop has happened. Down 14 gets printed. The control of the recursion is right here. Down 14 gets printed, return happens. Return happens to the same place from where it was called, line number 4. Stack.pop has happened. Down 12 gets printed. Return happens. The return happens to the same place from where it was called, line number 4. This has popped out. And now, down, flow of the recursion is right here. Down 8. Root is right here. Down 8 gets printed. Return happens. Return happens to the same place from where it was called. It was called from line number 2. The call stack is empty. All the function call is complete. This is the print statements that we will be print. Recursion returns to the same place from where it was called. 1:1 mapping of the parameter happens. And recursion doesn't stop till the time the call stack is not empty. And this was the flow of the recursion till now. Anybody, any questions till now? All right, if you were observing it carefully, can you tell me what was the maximum number of calls inside the call stack or the recursion stack right here? What were the maximum number of calls inside the recursion call stack over here?
5.
At any point? 5.
5.
All right, 5. So can you tell me in terms of this tree's parameters or tree's input variables, what is 5 over here? For example, for this, yep, height of the tree of edge. So number of maximum calls inside the recursive stack at any point was h. That is, we had 5. One was functional call on that. That's right. Height of the tree is the maximum space inside the recursion stack that we took. All right. Before moving forward, let's validate whether our understanding of flow of recursion is completely correct or not.
In this case, isn't the height of tree 3? Because we are going left
1, 2,
thrice,
3.
1, 2, 3. So
1, 2, 3, 4. Depends how we are defining the height. You want to define height as height minus 1, you can do that also. So if the interviewer says that, okay, the depth of the tree over here, just if you, separate question. If they say, tell me what is the height of this tree?
3.
Or depth. Somebody can say 4. It's a 4-level BST.
Hmm.
All right. It's the way that you are defining your height. Is new array list. I'm not going to use this array list. I'm going to return a wrong answer over here for the Inorder traversal. Don't worry about that. But let's make the tree over here. And if you see how I am defining the tree over here, or I'm writing the tree over here, then this is the way that you can do on lead code, or this is the way that going forward you will be learning about a concept of serialization and deserialization. But for now, just observe how we are defining the tree. 8. On the left of 8, we have 4. On the right of 8, we have 12. Now the next node is 4. On the left of 4, we have 2. On the right of 4, we have 6. On the left of 12, we have 10. On the right of 12, we have 14. On the left of 2 now, we have 1. On the right of 2, we have 3. And it will keep showing you the tree that you have built till now. On the right of 6, on the left of 6, we have 5. On the right of 6, we have 7. And that's it. All right. This is the tree that we have. Let's write helper of root.left or function column root.left. Just replace our helper on the whiteboard with this Inorder traversal and system.out.print up system.out.print root.value and Inorder traversal of root.right, and below that print down statements. And for your sake of understanding, stack.pop over here, the way that we have written on the whiteboard, and stack. All right. So you should not be giving us because here they want the Inorder traversal. We are just using this problem for printing statements, all right, for understanding the flow of recursion. Okay, I forgot to do. Let me do one thing. Private void helper call on node root so that it matches with the whiteboard also. And I'll take these. If the root is equal to null, return. Helper. And we'll do the initial helper call on root just to print the flow of recursion. All right. It gives us a result is empty, But let's look at the print statements. Print ln. New line. New line. Okay. Let's try it. All right. Let's tally it with the whiteboard to see if our understanding of law of recursion and recursive stack is correct. Up 1, down 1. Good. Up 2. Good. Up 3. Same thing. Down 3. Perfect. Down 2. Perfect. Up 4. Perfect. Up 5. Perfect. Down 5. Perfect. Up 6. Perfect. Up 7. Perfect. Down 7. Perfect. Down 6. Perfect. Down 4. Perfect. Up 8. Perfect. Up 10. Perfect. Down 10. Perfect. Up 12. That is there on the whiteboard also. Up 14. Correct. Down 14. Correct. Down 12. Correct. Down 8. Correct. That is the flow of the recursion that we have. All right. Without understanding the flow of recursion, we will not be able to do normal recursion. We will not be able to do the backtracking. We will not be able to do DFS. All right. So understanding flow of the recursion, this is one of the most important lectures in the whole cohort, understanding the flow of the recursion. A lot of students think that, okay, at the code level, we will be able to understand the recursion. They are in for surprises later on. All right, always. If I remove this, then this becomes an in-order traversal. Left, processing of root, right. And if I print, surprise, surprise, everything will be in a sorted manner. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is not there. 10, 12, 14. And remember, why? Because our tree was, the tree that we had built over here or on the whiteboard is a BST. So this is nothing but, if I remove this is nothing but the in-order traversal. Quick question. If I remove this and I print this, what will be? What will be your comments?
Postorder.
It is a post-order traversal. So if I print this is nothing but the post-order traversal that we have. All right. In which left, right, root. Left, right, 3, root 2. This is nothing but the post-order traversal. Makes sense? So kindly understand the flow of the recursion. It is very, very important. Anybody, any questions till now? Result.add, root.value. This dot result. Just completing the in-order traversal problem over here. Okay. This dot result is given here. If I run this should be working fine. This, if I submit it, this should be working fine. This is the in-order traversal. In-order traversal is the one that we used for understanding the flow of the recursion. But let's come back to our parent problem of validating the BST. All right. One of the ways that I can validate the BST is that I just take this from here. Whatever we did over here, we put in inside the result. I create a resultant list over here. That's the way that I created over here. Private void helper of tree node root system.out print the result over here. All right. So if I do this in the helper call, I can take it from here. Remember, this is the Inorder traversal now that we have. Basically, Inorder traversal, and we print the result. It will be in a ascending order, right? For any of the trees. For this tree, that is 5, 1, 4, 3, 6, 1, left, root, then 1, 5, 3, 4, 6, which is not in a sorted manner, so it's not a BST. But if we take this tree over here, this is a BST, it will be printed in a sorted manner. It will be printed in a sorted manner. And that's what should have happened. But we are using an extra result list over here. And that result will be containing all the elements of the BST. We are using extra space, even though that extra space is not required. So how do we do it without using a resultant list? How do we do it without storing all the elements inside the result and still do the Inorder traversal only to validate whether it is a BST or not? Anybody, any suggestions?
We check if the root value is greater than the left and smaller than the right, and then we recursively call is valid BST.
So means Inorder traversal will not work. So you're suggesting a new algorithm over here, right?
No, so you can do that in order. Like we check if left is smaller than the root and is BST on the left.
What is Inorder traversal? In that we print the left and then the root, then the right, right?
So we go on to the leftmost node.
Okay, let me modify my question. Can I do the Inorder traversal without using the list, without storing the elements inside the list?
Can we do Inorder traversal without storing in the list?
Yeah.
We want to print everything, right?
Do I need to print?
So just we want to do is valid BST, right? Or
do I need to print, or do I need to store all these elements in a list? Is there
solve
any
this?
way? When I'm saying that can we do something, it means we can. Yeah, what are you saying? Go ahead. I might. Yeah.
So for is valid BST, can we do this without storing it in a list, right?
Yeah. Can we do it without storing it in a list? Without storing the Inorder traversal in a list?
Yes.
Yeah?
What I'm suggesting is like we compare the root with the left value and the right value of the root.
We process the root. Okay. Then?
And then we call on the left should be also a valid BST and right should also be a valid BST.
Root.left, we call a function call on root.left, and then we call a function call on root.right. Correct?
Yes. Yeah.
Is this Inorder traversal then?
No, it's pre-order traversal.
So we can do it with pre-order traversal. What you want to say over here is that with Inorder, what I'm asking over here, with Inorder, it is not possible. because we were on a discussion of in-order traversal, right? We can store the elements in a resultant list. So should we come to a conclusion that if we are doing in-order traversal, we will have to store the elements inside the list only. Neither we'll have to abandon in-order traversal and we'll have to go to pre-order traversal. Will that be a correct statement if I make that?
Yeah, so far I'm not able to find a use case where we can do it with in-order traversal.
Okay.
But
Anybody
needs
else? Anybody else? Okay, if I have the in-order traversal over here, if I have the in-order traversal and I'm storing it in a list, then it is 1, 2, 3, 5, 4, 5, 6, 7, 8, 10, 12, 40. Correct? If I do an in-order traversal, I store the elements in a list like this. How do I check whether this list is ascending in nature or not? Whether this list is sorted. How do I check that?
Just
compare it
iterate
with the
through it.
list.
Just iterate through it and iterate through it. Like, I'll go over here. Now what? Then I'll go
Now
over
check.
here. At 2, what should I
No.
check?
Check its next element if it is greater than just 1. If it is not, then
Left value
If-
should be
If its next element 3 should be greater than 1.
greater than 2, like greater than 1 unit.
2.
Yeah.
Too
I missed the
complicated,
part that I missed the part that we might have missing numbers. I missed that part.
Forget about that. I am giving you a list, a simple list. This is the list, universal. Tell me whether it is sorted or not. How would you check it?
The first and the last most element. The first
and the last most element. If first one is smaller, last one is greater, then the whole list is sorted.
We have to check the next element is less than the previous element, then it's not sorted.
Yeah, let's have current element and the previous element. If 2 is greater than 1, then we move forward. If the current element is greater than the previous one, just that thing, there is no rocket science over here. If you want to check whether the whole list is sorted or not, in a brute force manner, if you want to check whether the whole list is sorted or not, just check 3 is greater than 2, 4 is greater than 3, 5 is greater than 4, 6 is greater than 5, 7 is greater than 6, 8 is greater than 7. This is the way that we can check, na? Or I can say I can have 2 pointers. And this middle pointer over here, if this is current pointer and this one is previous pointer, current is greater than previous. Then move both the pointers. Check 4 is greater than 3. Move both the pointers. 5 is greater than 4. Move both the pointers. 6 is greater than 5. This is the way that we can check whether the complete list is sorted or not. One current pointer, one previous pointer. Now, why do I need to store all these elements inside a list? I can just move the pointers on the list, on the BST, on the tree itself. Now, I have the root, which is my current, and one previous pointer to it. That is what is the previous element. Why do I need to store all the elements over here? I just run 2 pointers on the whole tree only. The tree is giving me this list now. So if I am able to mine that before 1 there is nothing, when we are at 2, just compare it with the previous element. I'm saying previous, I'm not saying left. Don't start making assumptions. I'm just trying to mine what I will do it on list. If I had stored all the elements in the list, how would I check whether the list is sorted or not? Just keep checking 2 elements. 2 is greater than 3. 2 is greater than 1. 3 is greater than 2. 4 is greater than 3. So and so forth. I don't need to store all these elements inside the list. I can. These elements are coming from BST only. Na? I can do the previous and the current on the BST itself. So initially, remember this will be printed. This was the print of the in-order traversal. At that time, I can have a previous at the null and current at initial root which will be printed or which will be processed was 1. At that time, I don't need to check 1 with the previous because there is no previous to the 1. I don't need to check whether it is greater than. There is no previous yet. But once 1 is done, I'll move the previous pointer to the current position. And current goes to the next position. What was the next position in the Inorder traversal? What was the next root which was printed? It was 2. Current. When 2 comes out of the stack, or 2 is about to be printed, at that time I'll just take it with the previous. If everything is fine, that is 2 is greater than 1, then I'll move the previous to the current position. And what was the next node which was printed in Inorder traversal? Was 3. My root will be here, my current will be coming right here. I'll check the current with the previous. Is 3 greater than 2? It is greater than 2. I'll move the previous to the current position. And current will be then at 4. Just check 4 is greater than 3. Yes, it is greater than 3. Then move the previous to the current position. Next position of current is what? 5. Just check current with the previous. Is 5 greater than 4? When it is fine, move the previous to the current location. Current to next location. If at any point during the tree there is a breach, we'll say that we have found a breach. It's not a valid BST. We can store it in a flag. All right. So let's try to do it without storing inside the list. We can. This list was coming from the tree only, no? And how do we check? This is current. This is previous. Current. Previous, current. Exactly this is the movement that I am miming on the tree. Move the previous to the current location, current to next location. Move the previous to current location, current to next location. Keep checking whether they are breaching or not. Move the previous to current location, current to next location. Move the previous to current location, current to next location. All right. This is what we will be miming. If I try to run this, if I try to write code over here, I just need a previous pointer to validate a BST. I don't need to store it in a result. So let's have a private tree node previous. All right. And a Boolean flag. And I'll do a helper call. Or you can call it Inorder call. Inorder. What kind of call I should be doing? Will it be a Boolean based recursion? Will it be a void based recursion?
Boolean.
Boolean based recursion. Let's do void. Private void Inorder traversal on tree node root. All right. Base case logic. In the logic, in the Inorder traversal, what do we do? Left in order of root dot left. In order of root dot right. And we have to process the root in between. Na? Process root here. How do we process the root? If my root dot value, which is current also. Root dot value is lesser than or equal to previous dot value. In English, it means what?
The root is smaller than the left child.
So I just said that, okay, current, previous, there is no left, there is no right. Is 7 over here and 6 over here? Is 6 the left child of 7? This is Inorder traversal. You are still stuck onto one of an algorithms which we are not even doing, which we are even not attempting. We are just traversing over this list and we are checking whether the current is greater than the previous or not. If current is not greater than the previous, if rather than 7, if we have 2 over here, then what? Return false. This is not a valid BST. That is what we are trying over here. If my root dot value is lesser than or equal to previous dot value, root is current. If current value is lesser than or equal to previous dot value, all right, at that scenario, we have a breach of BST. All right. And we'll make the flag is equal to false. I cannot compare the initial one. If previous is equal to null, it means we are right here. Current was equal to 1, previous was null. Then previous came over here, current went over here. All right. So 1 should not be compared to anything because there is no previous value to it. And remember, by default, the previous is getting initiated over here in the global with null.
Previous is not equal to null.
Previous is not equal to null. All right. Flag is equal to false. And the base case, if my root is equal to null. If at any place we have a breach, the flag will become false. I'll make the initial flag as true. If at any place it has breached the valid, it's not a valid BST, we'll be catching it with flag is equal to false. And root return true. Not true, return the flag again. If I try to run this code now, let's see what mistake that I'm doing.
Need to change the previous value?
Yeah, we need to change the previous value. My bad. Previous to current position. Move the previous to the current position. Before doing the right recursive call, once we have compared, remember this is what we have to mind. Current, previous. Once we have done the comparison, move the previous to the current position. This is what Imran is pointing out and he is absolutely correct. Then move the current to the next position. Current, in this scenario, I don't need a separate current pointer because root is my current. Root is my current node that we are working with. All right. If I run this should be working fine. Oh, not current, root. Working fine. If I submit it, this should be perfectly accepted.
Here, like we are making the flag as false, right? So the recursion will still keep on going. I mean, it won't stop at the false.
We'll come to that. That's a good question. Good, great question. All right. Anybody, any questions till now? I want to bring this as the first test case. Okay. And the second test case is 1, 2, 3. All right. What Pulkit is asking is a great question. If I do system.out.print, root dot value over here. Apparently, we are processing each and every node. So in the pre-order manner, all the roots will be printed. And they will be printed in pre-order manner, right? If I'm printing it right here, they will be printed in the in-order manner. This is pre, before the left now. So all the nodes will be printed 8, 4, 2, 1, 3, 6, 5, 7. Whatever is there on the whiteboard, everything is printed. All right. Or let me print it over here at the in-order level so that it is in a sorted manner. Okay. 1, 2, 3, 4, 5, 6, 7, 8. All right. So I'm printing it over here so that there is no confusion. Okay. So all the nodes will be printed. Imagine if we have a breach over here, rather than 1, if we have 7 over here, like 100 over here, rather than 1, if we have 100 over here, or 10 over here. Good. And rather than 10, we have 11 over here. Okay. Is this a BST now? Anybody? It's not a BST. So we should be getting a breach. And correctly, we are getting a breach. Where is the breach happening over here?
10 is like
Greater than.
great.
10 is greater than 2. Or 2 is smaller than 10. No? So it will be getting a caught over here when the root value will be equal to 2 and the previous value is equal to 10. At that time, we will catch it that there is a breach. So the breach has happened over here. But if I print the elements over here, what Pulkit is saying, all the nodes will still be printed. Recursion will go to all the nodes. And not surprisingly. Why? Because whatever has gone inside the recursive stack has to be completed. Function call on 8. First function call was function call on 8. In the recursive stack, we had at the bottom function call on 8. Then function call on 4. Then function call on 2. Then function call on 10, so on and so forth. The breach has happened at this place. Still, why are we recursing on 10 and 14s and 12s? 11 now, okay. Why are we going to 11s and the 14s and 12s? And why are we checking the 5s and the 7s? If the breach has happened here only, why do I need to go to the 6 and the 5s and the 7s and the 11s and the 12s and the 14s? Can we do something that we can save some of the recursive call? Save some of the recursive. How do I modify it?
Check the flag in the first condition.
Check the flag in the first condition. That is line 26. Right here. If the flag is equal to false, then what?
Return for like do nothing, just return.
Just return. All right. Now this, what we have done till now is the dump brute force recursion. It's non-conditional recursion over here. As soon as I bring that check if the flag is false already or not, then that is conditional recursion. If the flag is false now, you don't need to further recurse, is what Imran is saying in English. I don't need to do the further recursive calls if my flag is equal to false. Or I can do it like this. Flag is equal to true. Then only do the right recursive call. Then only do the right recursive call. Or I can write it like this. If the flag is true, then only conditional recursion now. If the flag is true, then only do the left recursive call. If the flag is true, then only do the right recursive call. If I do and run it now, then I will be able to save, surely able to save some of the nodes. All right. Now, which are printed is 8, 4, 2, and 10 also. That's it. 8, 4, 2, and 10. Earlier one was non-conditional recursion. This is conditional recursion. That if the flag is true, then only go towards left. If the flag is true, then only go towards right. If the flag is already false, why should I go towards the right recursive call? I don't need logical. And this is the same as what Imran was suggesting, that if I can put this condition in the base case also, or flag is equal to. If the flag is equal to false already, return. Don't go further. Don't do the further recursive calls. No need to do the further checks. If breach has happened, I don't need to go to the further nodes. If I do that, I'll be printing same. Now I have moved that condition inside the base case. This is called conditional recursion. We will be doing it at many places where we will be doing non-conditional recursion, then we'll be doing the conditional recursion. Is there any other way than checking the flag? Can I do this? The interviewer says, oh, it's working, perfectly working code. What if I put the return statement over here? How many nodes will be printed over here? Remember, in the earlier case, 8, 4, 2, and 10 were printed. Now the breach is still happening at 10 only. And I put the return statement over here. If flag is good, false, return. If I put the return statement over here, what will happen? Just take a wild guess. Although you should not be taking a guess because it is based upon the recursion rules that we had learned.
After 10, nothing gets printed. Like till 10.
Oh, till 10 only, 8, 4, 2, 10. And why? Why do you think so?
Not going to the right tree after 10.
Will not be going to the right tree. Anybody else? How many nodes will be printed over here?
Only 3.
Only 3. 3 nodes. 8, 4, 2.
8, 4, 2. Yeah.
Okay. Anybody else?
So we will go. We will start.
No, don't worry. Just tell me how many nodes will be printed.
I think all of them would be printed.
All of them will be. That's a very revolutionary. All right. All of them will be printed. And the reason?
Because in the function call, we still have all the traverse, basically the function.
Good. Good. Let's run it. All right. It should have given us a correct answer. It has given us a correct answer. But the good thing is that we should be looking at how many nodes are printed. 10 only. 4 only. If I print the return statement over. But is Mayank incorrect over here? Let's try to make this as 1. And this as 13. The breach has happened over here. Correct? At this place, the breach has happened. If I try to print, how many nodes will be printed over here? Okay, let me think about a test case. Not 13. 13 is too much. Okay. It's the previous. Is this a BST? If I run this, should it be giving you a BST? Should be giving us a false. It's not a BST, right? And where is the breach happening over here? At this 2. At 2. All right. Or let me make this as 3 only and make this as, rather than 1, let's make it 3. Where is the breach which has, oh, no. Yeah. The breach has happened right here, no? At this 2 and 3. Right here. So if I take that, the other one was really big. That's why it was, printing 4 of the nodes only. But if this happens, the breach has happened right here, 2 and 3. But still it is printing what? The 12s and the 11s and the 14s also. This side of the tree also. Even this side of the tree, it is printing. If I make it 5, just for sake of simplicity, if I make it rather than 3, if I make it 5.
The line 31, less than or equal to preval, it has to be less than, right?
Just a moment. If I have, rather than 5, let's have 4 on it. All right. But what will be printed over here? All the nodes, still. Still the 12s and the 11s and 14s are getting printed. Why is the 12s and 11s and 14s are getting printed even though I have the return statement over it? So what I'm trying to say over here is, in some of the cases, if I have the breach right here only, at this place, why are we going to the 6 and the 5s and the 7s and the 11s and 12s and 14s with this return statement?
In the function call, when we were calling 4, there was left of 4 was 2, but that's not where the breach happened. So we went to Inorder for left, right, and so this is still in the function call. Like,
all right, let's see it on the whiteboard. Let's not have 10 over here. Let's have 3 only over here. Recursion call stack. It started from here. All right. Functional call on 8. Functional call on 4. Functional call on 2. Functional call on 3. Functional call on null. Right. So firstly, null is out. The first node is 3, which comes out, or the recursion stack in the in-order manner. We compare it with the previous. Previous is equal to null. Move the previous to this location. Then we do the function call on the right. That is out. Null, null, both are out. Function call on 3 is out. Now at top of the stack, at the in-order level, we will be printing 2, right? So 2 is the node. That will be compared with, this is the root, that will be compared with the previous. We have the breach. We make the flag equal to false. And after that, we have return. It's a myth that the return will be completely stopping the recursion. Students who think that only 8, 4, 2, 3 will be printed, they are thinking that this return will complete the functional calls. It will stop the recursion. It doesn't. It is against the 2 basic rules of recursion that we did. One, whatever has gone inside the stack will come out of the stack, surely. The call stack does have functional calls still left. That is what Mayank was pointing out towards. That I still have the functional calls left inside the recursive stack. The second thing that we made assumption is that return will not be taking us further. Recursion will stop over here is again a breach in the rules. The first rule of recursion was return returns to the same place from where it was called. That's it. Doesn't mean that it completes all the functional calls. It just completes that functional call only. It will be returning to the functional call of 2. That's it. Functional call of 2 is out, then the functional call of 4 will start. So the purpose of this return statement is returning to the same place from where it was called. That's it. It was not stopping the further recursive calls. The further recursive calls will still happen. If you are assuming because of this return, the whole recursive function will be complete, then you should have said the same thing for this return also. That we hit the return and we are done. No. Just like the way that this return behaved, that it returns to the same place from where it was called, this return will also be doing the same thing. It will be returning to the same place from where we called it. It will go back to the functional call of 2 that will be popped out, and still 4 will be further running ahead. The further, once 4 is complete, 4 will be out, function call on 8 will be done, and then we are doing the right recursive call without any condition. Without any condition, we are doing the right recursive calls. It will do the right recursive calls freely. Because at the further ones, there is no breach. Thinking that this return statement will be able to do the conditional recursion is a wrong basic that you might have assumed. If you have to do the conditional recursion, then you have to do flag equal to false. You'll have to do the conditional recursion like that. Now I'll be having 8, 4, 2, 3 only. That's it. 4 nodes. I want to do the last basic of recursion today. And then we'll be stopping. Firstly, it's a myth that if I have a Boolean over here, I have to do the void function also as I have to do the recursive call as Boolean also. All right. I can do Boolean based recursion. I can do void based recursion also. In all the problems that you have done, int based recursion or Boolean based recursion, where you have integer, you thought that void will not work, void will surely work. In all the problems where you have seen void based recursion, there the Boolean or the int based recursion will also work. All right. So if I don't want to do it this way, I can do a Boolean based recursion over here. Return true. Thus converting into a Boolean based recursion. A Boolean towards left recursive call, and right recursive call is a Boolean right. Then return left and right. All right. If I want to convert it into a Boolean based recursion, I didn't do anything. I just put from the left recursive call, we are getting a Boolean. From the right recursive call, we are getting a Boolean. The rest of the things were kept absolutely same. If the root is equal to null, return true. If the breach has happened, return false. That the breach has happened. It's not a valid BST. I don't need a flag now. Works. If I submit it, this should be working perfectly fine. All right. If I do system.out.print root.value, how many elements will be printed over here? All the nodes. Remember, there is a breach right here. Still, all the nodes will be printed. So this is equivalent to non-conditional void-based recursion. Non-conditional void-based recursion. If I want to convert into conditional, then I can say that if my left is equal to false, then don't do the right recursive call. Return false. If I submit it, this should be accepted. But what's cute will be to see how many nodes will be printed over it. All right. If I do this, how many nodes get printed? 4. So this is conditional recursion, conditional Boolean based recursion, similar to conditional void based recursions. All right. Now I can clean this code a little bit. If I say that if my left is equal to false, that is, if this is equal to false, return false, right? Don't go further. Don't do the right recursive calls. Same thing. All right. Still 4 only. Submit it. This should be accepted. All right. Since this is, then I can return. A lot of times you have seen this code for Validate BST, but it is nothing but where we started with the void-based recursions. Slowly, just updating the code. All right. Still, 4 nodes will be printed over. This is conditional recursion only. Why? If the left is equal to false, return false. Don't do the right recursive calls. Cool. So we can do void-based recursion. We can do Boolean-based recursion. We can do void-based non-conditional recursion. We can do void-based conditional recursion also. But now let's see. We are going to cover one of the basics of the recursion again. Let's go to the void-based recursion again. Let's go to the void-based recursion. Let me submit. Okay, done. Hey, quick question, okay? Why do I need to have if I put the tree node previous over here? Is there any issue? Or the concept that we are trying to learn over here is that what all parameters I should be having in the recursive calls. Why do I need to put it in the global? Can I put it in the scope of recursion as a parameter of recursion? Can I put the previous as a parameter of recursion? If I run this, it doesn't work. Maybe I'm making some mistakes. Tell me what are the mistakes that I'm making?
You need to pass a value, like initial value for prep.
Null. All right. And previous over here. Probably the previous over here. Still doesn't work. Am I making some mistake? Anybody? What is my... Huh?
Flag is passed
Yes.
by value and not by reference.
Pass by value, pass by reference. Good. Okay. Yes, Vishal?
Isn't previous root every time you...
Previous is equal to root. Okay.
No, in the line 28.
Previous is equal to root. Okay.
Okay, yeah. We won't need line 34 anyway.
Okay, still doesn't work. Okay, if you are saying this, then you are missing one of the things. Was I doing this? That when I went to 4, I'm making the previous of 4 is equal to 8. Or when I'm going to 2, the previous of 2 should be 4.
No, we are not doing that.
We are not doing that. So if I say that, okay, the previous is previous itself, still doesn't work. You can do this. You do anything, it will not work. What is the basic mistake that we are making? We make it root, okay. Yes, Tanya, go ahead. What were you saying?
You're passing flag by value.
We're passing flag. Flag is not passed over here. I didn't change anything about flag. I changed
Oh, sorry.
previous
You're passing previous by value.
by previous by value. And what does it lead to?
We don't retain the value of previous.
Perfect. Perfect. That's a great. All right. This is by value and by reference concept, and it is very imperative. All right. You might be giving a working test, working code in your recursion. You can be giving any of the recursion. If the interviewer catches you at the by reference and by value concept, the game is done over here. All right. You might be even optimizing that with repeated subproblems, and you have implemented DP. Till the time you will not be able to get the by value and by reference concept, you will be out. And if you are an interviewer in the normal recursion in the Inorder Traversal or Validate BST only, just please do check that by value and by reference concept. It is in too many production systems in a lot of libraries, for example, React everywhere, by value by reference concept. What is actually happening over here is 1, 2, 3. If I have the remember 1:1 mapping now, helper of pre-node root and pre-node previous. We have this code now. Let me take this example right here. 1, 2, 3. And what are we doing? If my root is equal to null, return. And then helper of root dot left. You take the previous as previous over here. You take the previous as root over here. Doesn't matter. The problem is not what you are taking over here. The problem is by reference, by value. Helper of root dot right and previous. Here what you are doing is previous is equal to root. Here you are checking if my previous dot value is greater than or equal to root dot value. Flag is equal to false. All right. In the code, let's run it along with the code. Test cases 1 to 3. See, if I submit it, it gives me the test case 1 to 3 is correct. Means I should be expecting a false. But it is telling me that it is true. That this is a valid BST. This code right here that we have written, let's call it root. This code that we have written over here is telling us this is a valid BST. It's not a valid BST. What is happening over here? Remember, draw the recursive stack. Functional call on 1 and the previous is none. All right. This is the very first call. Is my root equal to null? Is my root equal 1 equal to null? No, it is not equal to null. Then we go over here. All right. Functional call on. We come over here. Roots left. That is 1's left. 2. And we made the previous as 1. It's fine. Firstly, we should not be making it. We should not be comparing 2 with 1. We should be comparing 1 with 2. 2 should be compared with null. So let's change it to previous. Let's keep it null only. Is my root equal to null? No. We come over here. Roots left. Function call on null. And what is my previous? Null itself. Is my root equal to null? Yes. Returns to the same place from where we called it. This is how. So 2 gets compared to null. And we don't compare it. Why? Because we were checking it right here that previous should not be equal to null. Doesn't happen. You made the previous is equal to root. You took the previous right here. And then you did the right recursive call. Functional call on null, null. Out. Both left and right recursive calls of 2 are done. Your previous is still at 2. Then you took this. This is out now. Return happens, return. We return to the same place from where it was called, right here. When the stack.pop has happened, what is your root now? 1. What is your previous now? 1 is to 1 mapping. No? Root is 1. Previous is what? Null. Your whole jing bang of making the previous is equal to 2 over here, it went, the previous was made equal to 2. There is nothing wrong. The problem is whatever goes inside the stacks will exactly unfold the same way. Now, when it unfolds over here, stack.pop has happened. 1 is to 1 mapping has to happen. Root is equal to 1. What is previous? Null. Over here, the previous is null. 1 is never compared to 2. 1 is compared to null. And that is not compared. Why? Because in the if statement, I have a if previous is equal to null, don't compare. So I don't catch the breach over here. I should have caught the breach over here at 1, 2. Now 1 is getting compared to null. You do anything. Make it previous, make it root, make it null. So what? 1 has gone inside the recursive stack. Whatever you came with nothing, you go with nothing. Similarly, inside the recursive stack, whatever you came with, you will be unfolding the recursive stack as it is. Now 1 is getting compared to null. It doesn't get compared. And you don't get the breach only. Then you go towards 3. 3 is already greater than 1. Done. You never catch the breach. So if I print over here, in this test case over here, in the second test case, if I see over here, system dot out dot print root value and system dot out dot print ln the previous. You will see that 1 is getting compared with null. over here. If one is getting compared with null over here, then the whole game is over. You make it root, you make it previous. 2 will get compared with null, 1 will also get compared with null. Because whatever has gone inside the stack will come out of the stack as it is. 1 will get compared with null. This was not happening in the earlier scenario. If I put the tree node previous in the global, it doesn't go as a parameter of recursion. Then let's see this. Now let's see that 1 is getting compared to what? 1 is getting compared to tree node this, which is actually equal to 2. If previous is not equal to null, then write the value of previous. If it is equal to null, then print. Oh. Right. 2 will be compared with null, 1 will be compared with 2. If I have the previous in the global. Because in the parameter, the previous is going by value. And when the recursion stack unfolds, it unfolds the same way. Makes sense? Hence the breach. So this is the parameter of recursion versus the global variable. Cool. We are done with the class. Anybody who has question can stay. We'll carry on with the lecture from here only. We'll be doing more recursion. We'll be going into the nitty-gritties of recursion. And we'll be doing a lot of vertex scenarios. All right. Anybody, any questions?
Can you just summarize in like a single sentence? Maybe the last issue was we were passing like value and we are not able to retain.
It is 420, then it is 840. It is 840. It is 1220. Node 420, 840, 1220. It is going by value. So it unfolds by value. That is, null has gone, it will be null only. Then it will be whatever the next node, 840. All right, whatever that node is. All right, it is 1220, whatever that node is. If you are putting 1 as null, functional call of 2 as null, functional call of 3 as another node that is 8. It is this 3 node, this null, this null. All right. But if you put it by reference, if you put it a pointer on it, that is, you put it in global. 3 node, a pointer on it, previous. All right. I'm using the syntax of C++ over here just to show you. Then it doesn't need this. We don't need to do this. This is basically globalizing the variable. Then I am having a single reference. All right. If I have a single reference, that is actually equal to single reference, then 1, 2, 3, it will be made as, this will be made as that reference 420 will be made as 2. Then 1 will be compared to 2. We'll further see it. Just leave this concept for now, for tomorrow also. All right. We'll revisit
even
this.
if we are passing the parameter's value, we can do something in the code, right, to make that work. I mean,
what can you do?
No, I mean, like just.
Yeah, probably is a very dangerous work. Probably is a very dangerous work. All right. You can do in some of the scenarios, but not in all the scenarios. All right, Pulkit. What you are trying to say is, I want to go wrong on the basics, but I want to still find a way out, find a hack out. All right. My question is, why do you want to go wrong on the basic? You can in some of the scenarios. All right. But don't get into that habit. Because somewhere you'll be burnt. Make sense, Pulkit?
Yeah.
We're done with the class. Bye, guys. Have fun.